Alright, solve for x. Everybody solve for x.
Oh, I knew that's what
Yeah, I hope everybody can do this. We're gonna find out. We're gonna find out.
Okay. I didn't read the couch. Give me a second.
That's why you.
It's good.
Looks like there's gonna be two answers. You guys getting the two answers?
Yeah, that's right.
Getting the two answers? You guys trying to put out?
That's
Bomb.
What'd you get? What'd you get?
Bomb, Mr. Griffin.
Wait,
Really?
that's a good one.
You said.
Huh?
X equals 7 and 1 thing.
Okay.
Is it plus or minus?
No, I think it's what you said. Yeah? Here, let's try this out. 1/3 and 7. Exactly. You guys got it. 1/3 and also 7. Okay. Guys, could you, if you want to, you could take each of those answers, plug it back to the original statement at the top, and it would make a true statement and come out equal to 4. Yeah, you do that too. Here. You guys want another one?
I'm also not use my calculator.
Yeah. Go back to
I need to calculate. Need to calculate what's up. It's a weird number. Hold on. Let's say there's something variable. I don't like that.
Does x equal -2/7 or 4?
So we got. All right. Here, Lincoln got. Lily got. Let's check it out.
I go with that too.
Oh yeah, -2 over 7 and 4. That's exactly what you guys said. So you guys can do some algebra. And of course, if there was no numbers, you guys could do just variables like mgh and 1/2 mv squared, and you guys could go.
There is 2 steps. I was so confused.
All right. Well, okay. It's whatever had a question I got. All right. Okay. Guys, could you guys say B is equal to C sine theta, and A is C cosine theta? Okay. Guys, how can you solve for this theta right here?
Inverse.
Yeah, inverse tan of B over A is a good choice. You can do some other inverse tricks too, but you have to do an inverse trig, don't you? Inverse trig.
No. No, I used to do that.
Guys, write the 3 kinematic formulas. Yes, you have them available on the page, but I think it's good if you do know them. What? How did this go? You guys know the 3 kinematic formulas? It's okay, I got a little hint on the screen for you guys. I'll put some units. Okay. So, looks like even before I reveal the formulas, looks like in terms of units, you got meters here. Guys, what's meters per second times meters? That's meters. What is meters per second squared? I bet this times seconds is going to be squared. Would this also be meters? Can I say meters plus meters is meters? How about this next line? Meters per second, meters per second.
Wait.
This is also meters per second at the end.
Oh wait.
Guys, see how that?
You know, I just don't remember which ones get done.
Is that what you guys came out with?
Yes.
And then with my units, like this one meter per second, it is being squared, which would match this meters per second squared. Okay. Guys, if you want to add terms together, don't the terms have to have the same units? Meters plus meters is meters. Meters per second plus meters per second is meters per second. Meters per second squared. Or sorry, meters squared per second squared plus meters squared per second squared is meters squared per second squared.
So you had to write some equations from this.
Remember that lab? Took you guys out on the balcony? How'd you guys solve for the blast speed? Based on H and D. So you measured the height of the balcony. You got so many meters tall, and then you blasted the bouncy ball, boing, and you spotted where did it land on the ground, and then you took either meter stick or trundle wheel. So okay, some distance D out from the edge of the cliff. From that, you were able to calculate what was the blast speed of the launcher. Go ahead. I solve it in terms of variables. Looks like I got a 3-part process.
Hold on, I gotta solve them.
For guys. Okay, so what is the blast speed in terms of H and D? What is the blast speed in terms of H and D?
D over T, okay, so yeah. D over. Yeah.
D times.
Just to rearrange root of D over D.
I would rewrite that as D times root D over T.
Oh, yeah, here's something about a fraction, sounds good. You guys said there's gonna be a G somewhere in the mix. Because I imagine if I took this to the moon, yes, if I take this to the moon, would it land way further out? Yeah, for the same launcher, it definitely would. Huh.
T is the rooted. Is doing. Special things.
Alright, and what'd you guys get?
D over 2.
Okay, alright, let's check that out. Here we go. Alright, so I'm gonna start with the vertical here. Okay, now, you guys know that's one of your kinematic form. Notice I left out the V naught T bit, because guys, if you're blasting it, it is moving really fast, but in what direction? In the horizontal direction? Okay. Is everything in red here strictly vertical? So what's the initial velocity in the vertical direction? 0. Same as if you just dropped it. That's why I can drop the V naught T part, right? Okay. Alright, and I'm gonna go through a series of steps and solve for what right here?
D.
T, yes. Solve for T. Right. So now I know the time of fall. It's the same time of fall as if you just dropped it. Or if you throw it horizontal, hits the ground same time. Right. Alright. So I'm gonna hold on to that. Now what do I set up over in the side box?
The other one.
Yeah, how about the horizontal? Oh, now what? Bing. Right there? Yeah. Okay, so I can sub that in there. Now, it looks like I'm dividing by, well, what ends up being a fraction. It's in the square root. Okay? Because if you divide by a fraction, can you flip that fraction and multiply it instead? Flip and multiply? Right. And that's why this 2h on g flips and becomes g over 2h. Aha. Yeah. Right. If you left it a fraction within a fraction, AP would still give you credit if they asked you this question. Right. So if you, so if you simplify a little bit different, it's all right. All right. Well, you guys are finished to write that one. How about this? What if you have different launchers? You guys see, you got different launchers. Right. You have the T-Max 5000 and the Blaster 8000. We got all these different launchers. And one launcher blasts. See this D right here? Twice as far as another launcher. Guys, if one launcher blasts twice as far, twice the D, what's the ratio? How much faster is it blasting?
Twice as fast.
Twice as fast. Because that's a direct relationship, isn't it? Between this V and this D. You see it? How about this? What if well, okay, yeah, you can play with that. Okay. All right, so you guys good?
Yeah.
Let's keep going. Ooh, car brakes just stopped. I don't know why the color's all messed up. I copy pasted this from one presentation to another. Yeah, anyway, I guess we got a blue car today. Got a blue car. Right. Okay, let's make a free body diagram on this car. What's one force on this car?
Gravity.
Yeah, its own weight. What's another force? Normal force. And yeah, it is braking to a stop. So between the tires and the road, that was what that force would be, right? That looks like a nice free body diagram. Right. Now, at what rate is the car slowing down? You do need a character that's not on the page yet. What character do you also need? Yeah, mu, coefficient of friction. Okay. If there's no coefficient of friction, then the car would just slide forever, go all the way around the earth. Yeah, so you need a coefficient of friction somewhere in the mix there. Yes. Substitute in a coefficient of friction. Walk around. Something got this right. Ah, Logan got it.
Well, I knew how this one.
Alright, Logan got it.
You're locked in.
Close. Schlupp got it.
Negative U weights.
Ooh, it sounds like Austin got it. Yeah, you're on the right track. Yeah, you're on the right track. Yeah, so you guys are good, you're good there. Nicholas got it. All right, so you guys got it. Some of you guys are on the right track. We'll just have to do a few more substitutions. All right, you guys ready for this? Here we go. So here's Newton's second law. Net force results in mass times acceleration. Oh, guys, what is the net force in this case? The friction force is the net force.
Exactly.
Okay, so I said that in. Oh, because what is this friction force in terms of this normal force?
MG.
Well, yeah, mu n, right? Or mu Fn?
Yeah.
Okay, and now, yeah, there you go. You see the next one. Normal force is equivalent to mg. Okay, as long as you have a level road, which is oftentimes the case. Yeah, there you go. Yeah, so car slowing down at that rate. Yeah. Okay. Hey, you guys got the car braking to a stop. Right? And guys, it might not be a car braking to stop. It might be a block braking to a stop. You push a wooden block and it slides across the surface and brakes to a stop. Or who knows? It's good. All right. Yes.
Not the elevator.
Elevator time. Hey guys, let's have this elevator accelerating upward. So I'll give that to you. So it's not accelerating downward. Right? It's accelerating upward. How do you feel inside this elevator? Very light or very heavy? Heavy. Therefore, you guys draw the free body diagram of this guy standing on this bathroom scale. What force and also what force? What does it look like? All right, what did you guys draw?
Greater ups.
There you go. Weight down, normal force up, and the normal force up is greater than the weight down. So that there's a net force upward, hence you would accelerate upward. Okay.
They're accelerating upward.
Here, set up a Newton's second law on this box over here. Newton's second law.
I cannot. It is that.
Okay. And
No, that's not hard.
yeah. Elevator up here. Elevator. You're solving for the normal force reading. Guys, so the very last line says normal force equals. What is it in terms of mass, gravity field, and the overall acceleration of the elevator? Okay. So the very bottom line, what's the normal force? That's the scale reading. What is the scale rate in terms of M, G, and A?
N minus mg equals ma.
So the question is, what is the scale rating in terms of M, G, and A?
A does equal mg plus a.
In terms of M, G, and A. Alright, who knows the answer? Who knows the answer? What you got?
I was like, let me grab mine.
Yep, that'll work. That'll do it. Yeah.
M times G.
Yep. There's another way you do it. Yeah. So you say MA plus MG. You do M times, then in parentheses G plus A. Okay. So here's the derivation you should have come up with. There's the answer. Okay. Guys, suppose you reverse this, so you had the elevator accelerating downward instead. Would this normal force become very small?
Yeah.
So I think this weight would stay the same. This mg would stay the same, but this normal force would become very small. Okay. And then if you did a whole derivation, the end result would change how?
Minus a.
Yeah, would it become a minus right here? Okay. Okay. So the g minus a.
I didn't know what I was talking about.
Oh, here. I'll throw some numbers on this one. I'm gonna switch my screen over. Give you guys some numbers. Alright. Atwood time. Get ready to do an Atwood.
It's not an elevator.
You're really fast when it's all out.
Oh yeah. It's Atwood time. So this is a frictionless massless pulley. All our plastic assumption. Here, where's
Centripetal pulley.
something here?
Well, it's not relevant to the system.
Doesn't matter.
Now,
Don't look at it.
Like,
Don't look at the phone.
Stop looking at it.
alright, sorry, I'm looking for something here.
Stop looking at shit.
Alright, let's call this guy, 9 kilograms. Let's call this guy 7 kilograms.
I mean, it's.
There we go, 9 versus 7.
Wait.
Let's see, what is downward acceleration
I saw them totally do.
of the 9 kilogram block? Let's say how far
Oh,
Move. after,
Got 10.
say 3.0 seconds. Alright, let's say it's a really big outlet, very long rope there. Okay. And what else? Let's say tension in the string.
Look, this week, this is kind of.
So we get all those.
Oh, you gotta go.
Alright, let's do it this way. I'll give you guys a head start, and then I'll start writing a solution. But I want you guys to all beat me to the answer, so I'm giving you guys a head start right now. See if I can come up with some hints for you guys before I start writing anything. Okay. You can see how these masses are fairly similar, 9 versus 7. Okay. Do you think the acceleration is going to be more on the slow end or closer to pure free fall? Yeah, probably closer to 0 than 10 meters per second squared. Yeah, probably closer to slow. Ooh. Do you think the tension of the string?
Oh, I know it's.
Well, I know the weights of these blocks. Isn't it pretty much 70 versus 90 newtons? Guys, does the tension have to be somewhere in the middle of those?
You mean kiss?
Yeah. I'm gonna guess maybe, well, the midway point would be 80 newtons, and it's always a little bit less than that, so I'm gonna guess maybe 78, maybe 78 newtons. We'll find out.
Which one?
Alright, so I started
Second
at
part?
acceleration.
Yeah, okay.
All right, you guys ready to get solving? You guys ready?
I mean, I guess you figured I get it.
All right, here we go. Here we go. I want you guys to all beat me to the answers. You guys beat me to the answers. You guys got 90 newtons right here. And 70 newtons right here. Okay. Now this tension will come back to you. I'll call it FT, and well, I'll just leave it there for now. Okay. That'll be the last thing we'll solve here. Okay. All right, so I'm gonna set up acceleration for the whole system, which would also answer the downward acceleration of the large block. Is F net on the whole system approach over M total. Okay. You guys, from whole system approach, can I say 90 minus 70 newtons? 90 newtons minus 70 newtons, acting on 9 kg plus 7 kg. So I have a 20 Newton net force acting on 16 kilograms. Look at it. 1 point.
Right.
Oh, oops. I should ask you guys. How many guys got that? How many guys got that right there? Yeah. Lots of hands. Great. Yeah, on a spectrum of 0 to 9.8 meters or 0 to 10 meters per second squared.
I don't know.
Yeah, that's closer to the 0 end, just like we're thinking it should be.
No.
Ooh, how far after some time ago? Does that sound kinematic? Kinematic?
Yeah, you gotta solve for
Who solved how far? Who knows how far? What'd you get?
5.6 to 5.
You got what? 5.6
5.6
centimeters? 5.6 centimeters? Let's find out. Yeah, I'm hearing 5.6 meters. So x is 1/2 at squared.
Because it's not like, oh.
We're looking at 1.25
No.
meters per second squared. We're doing 3 seconds.
I'm gonna try this and see what happens.
0.5, 125, 3 squared. Yep, that's exactly it. 5.6 meters. You guys told me 5.6 meters? 5.6 meters. That's right. That's right. And tension of the string. Did we solve that yet?
I have a answer, I don't know if it's right.
What'd you get?
I got negative 78.75.
78.75? I'm gonna write that down. That's not about right.
I'm gonna write that down.
78.75 Newton.
Newtons.
Yeah.
So, yeah,
Right. We're gonna see. We're gonna see.
Yeah.
Let's go, guys, can I pick either one of these free body diagrams? Let's go, how about this one right here? Let's try this one, okay? Now, since there's more force down than up, I'll call down the positive direction, so let's do that. So I'll say 90 newtons minus the tension force. Oh, this is sum of forces equals MA, by the way. Okay. That's going to result in the 9 kilogram block accelerating at 1.25 meters per second squared downward, which I just defined as positive, so I'll call it positive. Okay. So just do F equals MA as it applies to a single block. Okay. Okay. Now, if I do a little shuffle here, add this over, subtract that over.
No, it's not.
90 newtons minus 9 times 1.25 newtons. 90 minus 9 1.25. Oh yeah! Oh yeah! It's like Justin knows what's going on.
You can get it without
Bing.
You don't need
That's
to-
it. That's it. Alright, nice job. Alright, you guys can solve that woods.
Yes, we can.
You guys give that woods. Alright, and then here's all the variable answers. Boom.
No.
Here's a modified version.
Who modified it?
Alright. You guys can handle the modified. Ooh. Well, here guys, let's do this one. We can do this one. Okay, so guys, what's the acceleration of this block?
The chance, the mg sine theta. Over
It- It is
G sine theta.
g sine theta. Hey, you guys remember that? G sine theta? Alright. You guys, we got 1 minute to the bell, so I think it's up right here.